This is an explanation on field due to surface charges. Now, what are surface charges? What is a surface charge? If you have seen the explanation on line charges, surface charges becomes clear. The charges distributed on a surface. What kind of surface? Any kind of surface, and we will see a lot of surfaces in this explanation, so let's keep moving on. The most important thing here is the charge distribution. Charge distribution. What is a charge distribution? The charge distribution of a surface charge is given as sigma, that is charge per unit area. What area? The surface area. For example, consider this surface charge. Now, it needs some explanation here. This surface charge is basically a sheet, like a sheet of paper, which is placed on the XZ plane. If you take into account the x-axis and the z-axis, this sheet of paper, this entire sheet of paper is placed on the XZ plane. This sheet goes to infinity in all directions. It goes to infinity in positive and negative x-axis. It goes to infinity in positive z-axis and negative z-axis. And the y-axis, if you may notice here, the y-axis is perpendicular to the sheet. And on the sheet, there is a uniformly distributed charge. On this entire sheet, here, there is a uniformly distributed charge. And since this sheet is infinite, we can never say what is the magnitude of charge. We can only say what is the distribution of charge. And what was the distribution? If you remember, the distribution was charge per unit area. So the charge per unit area on the sheet is sigma. Now, I want to find out the field at some point here on the y-axis. Let me specify the point. It could be 0, a, 0. This is the field on the y-axis. I mean, this is the point P on the y-axis where the field has to be found. Now, how do we find this out? So, the first step is step 1. Divide surface charge into line charge. How do we divide surface charge into line charge? Let's consider a scale, and I'll take up a charge here. And here also. So we have two line charges basically. This is a line charge, and just like the surface charge, this line charge moves from plus infinity to minus infinity, or minus infinity to plus infinity, as we would like to call it. Likewise, we have another line charge, same magnitude, and it is also from plus infinity to minus infinity. Now I have two line charges, and both these line charges are equidistant along x-axis. So let's say if this is x, this is also x, and since we have to take a small width here, we take this width as dx. And when we have divided our surface charge into line charges, it becomes very easy to solve, or let's say it becomes more solvable. Moving on to the next page. So we have x-axis, z-axis, and perpendicular to both these there is a y-axis. And then again, as we discussed, there is a surface charge. I'm drawing a very crude diagram now. There is a surface charge, and on that surface charge I have taken two infinite charged wires. Two infinite charge wires. Both of them are parallel to z-axis. You can see, not very good diagram, but okay, both of them are parallel to z-axis, and we want to find out the field at a certain point. Let's say at this point P. So this is 0, a, 0, and this is x and this is x. Now how do we solve this problem? In order to solve this problem, we do the following. We don't view from this angle. We view from, I'll show you the line of sight. We view it exactly along the z-axis. This is how we view it. So when you view it along the z-axis, this is how the diagram looks like. This is x-axis, this is y-axis, and the z-axis cannot be seen because you are actually viewing it from that direction itself. And you will see two thin charge wires. You also cannot see those charge wires just because your viewing line of sight is in that direction. And so we have x, and we have to find out the field here. Now it's easy. And what is the width of these two? The width of these two is dx, and the width of this is also dx, and we have to find out the field at point P. How do you find out the field at point P? It's very simple. For the left charge, the green in color, the field will be radially outwards. We all know that the field due to an infinite line charge is radially outwards. Likewise, for the red charge, the field is also radially outwards. The field is radially outwards. And we'll have the vector components or the vector summation of the red and the blue. The vector summation of the red and the green here, not the blue, red and the green here, to find out the net field here. How do we do it? So let me number them first. So let's say this is 1 and let's say this is 2. Likewise, 1 here and 2 here. Now we'll call this as field E2 and we'll call this as field E1. Now do you know what is the field due to an infinite charge? The field due to an infinite charge is E equals to 2k lambda by the distance r. And what is r in this case? This is your r, and in this case this is your r. So how do you find out the value of field from here? So let's start revising things. First of all, we didn't start the question with lambda. If you might remember, we had started the question with sigma. There was charge density here, but we now don't need charge density. We need charge per unit length. So how do we convert charge density to charge per unit length? How do we do that? So if you consider these two lines as thin wires, they have an area. Let's say their length is L and their width, we have seen their width here, their width is dx. So what will be the area of the wires? Let me write it here. Area of wires will be L into dx. And let's say, for assumption, although it will be infinite, but for assumption, let's say that the charge on one wire is q, the total charge from minus infinity to plus infinity. So what will be sigma equals to? Sigma will be equals to q upon area, that is L into dx. Now what is lambda equals to? lambda is simply equals to Q upon L, and L is infinite, we know that, there is no question about that, but we simply need Q upon L, and in order to find Q upon L we simply write it as sigma into dx. From the above equation you can easily see, in order to find out lambda you find out sigma into dx, so you replace it 2k sigma into dx upon, now what is the distance r? If you might notice that the point P here is at a distance a, and this distance here is x, so r is the hypotenuse obviously, so that will become equals to root under a square plus x square. Now we have to change the page. Okay, so we are on the next page now, and this is the x-axis, y-axis, z-axis cannot be seen because you are simply looking into it. Z-axis is basically coming out of your screen right now, and so are these two wires, the green wire and the red wires. They are also coming out of into your face right now, so you cannot see them, and both of them are infinite wires. That's what we know. Let me review it. Both of these are infinite wires. There's no question on that, and this is also an infinite wire. Now we know that the field due to an infinite wire was 2k lambda by r, and that got changed into 2k sigma into dx upon root under a square plus x square. Now this is the field. Do we need the original field or we simply need the components? Let's have a look at it. So this is the x-axis, or displaced value of x-axis. This is the y-axis. We know that both wires have same charges, both wires have same distances, so obviously the field components along the x direction will cancel out, and along the y direction will add up. So how do we find the field components along y direction? So you will notice that there is an angle theta here, so there must be an also theta here and theta here. Now what is the y-axis component? EY. EY will be equals to E cos theta. Now what is E cos theta? E cos theta will be 2k sigma into dx upon root under a square plus x square. Now what is cos theta here? You can see that a is the base and r is the hypotenuse, so cos theta, this whole term multiplied with this entire term multiplied with a upon root under a square plus x square. And what is the field EY that we are going to get? I'm going to write it here properly. 2k sigma a dx upon a squared plus x squared. And then we integrate it. Now I want you to understand at this point here that I am not multiplying this with 2. I am not multiplying this with 2. I am not multiplying this particular term with 2. And why am I not doing that? Because I am going to integrate it full means from minus infinity to plus infinity. So in that process, when I am integrating it from minus infinity to plus infinity, in that process the entire thing will be considered, including this green charge and the red charge. So we don't need to multiply it with 2, we simply have to take one component along the y-axis and then we'll have to integrate it, because on integration from minus infinity to plus infinity all the charges will be considered. So moving on, this was your field 2k sigma dx a upon a square plus x squared. Now what is varying here? The only thing that is varying here is x, and rest all the other are constant, so it will be 2k sigma a, everything outside, dx upon a squared plus x squared. and that x value of x will be varying from minus infinity to plus infinity, and that will give us E naught is equals to 2k sigma a 1 by a tan inverse x by a. Limits again from minus infinity to infinity. So you'll have 2k sigma a and a will get cancelled out. So we'll have tan inverse infinity, that is pi by 2, minus tan inverse minus infinity, that is minus pi by 2, and you will have 2k sigma pi by pi. And if we change the value of k, what is k equals to? K is equals to 1 by 4 pi epsilon naught. So you'll notice that pi and pi will get cancelled out, and 1 2 will get cancelled out from 4, so you'll get sigma by 2 epsilon naught. So what do we get from that derivation? We get the value of field Ey is equals to sigma by 2 epsilon naught. There is another thing that we also understood from that derivation. Let me draw it in the diagram. So this was your one line charge and this was your other line charge. The one other thing that we understood from that derivation was that the x components, since both these fields are same, this is the field E1 and this is the field E2, and since both these fields are same, why are these fields same? I'll discuss it again. Both these fields are same because the wires have same charges, they have got same distances, and the distance is also r from point P, so both these fields are same. Since these fields are same, the x components will cancel each other out. The E1x component will be in this direction, E1x, and the E2x will be in this direction, E2x, and they will be cancelling each other out. So the only components that we will be left with is the y component Ey. Now what is the interesting part about Ey? The interesting part about Ey is that it is independent of distance. Did you notice this? We wanted to find out the field at this point, 0, a, 0. Now, do you get a anywhere in this result? You don't. So, what is the interesting thing about infinite sheet that we find out? We find out that due to an infinite sheet, the field is always perpendicular to the sheet. Let me draw the diagram. The field is always perpendicular to the sheet. The field will always be perpendicular to the sheet like this. Due to an infinite sheet, the field will always be perpendicular to the sheet. Also, it will be perpendicular to the sheet below the sheet too. So field is always perpendicular to the sheet, and that field is independent of distance. No matter what the value of A is, the field is always going to be sigma by 2 epsilon naught. And that is the interesting part about an infinite sheet. So this is the next problem of surface charge. Field due to a disk. Field due to a disk at the axis. So you have to find out field at this point. Let me name this point. Let's say the point is P, and you have to find out the field due to a disk. And this is a disk. On the entire surface of the disk there is charge. We can say that the total charge is Q. Total charge may be Q and radius is R. So obviously surface charge density becomes sigma equals to Q upon area. And what is the area of a disk? That is pi r squared. So every time I told you need to find out the sigma. Now what was the step 1? Do you remember? In the step 1 that I told you in the last case, step 1 was divide a surface charge into line charges. Divide a surface charge into line charges. So from a disk, how can we find out line charges? We can very easily get a ring. Let's see. let's say this is the ring here, and this is the ring here, and I've got a line charge now. I can take the ring separately and then take the axis and same point P, and I can very easily find out the field due to the ring. Now how do we find out the field due to the ring? So first we need the charge on the ring. That's very important here, finding out the charge on the ring. So in order to find the charge on the ring, there must be some area attached to it, because the charge on the disk is distributed in the area. So we need a small area here. You cannot just take a very thin ring and be done with it. You need some area here. So what would be that some area here? So let's take the radius as x and the width of this ring, this very thin ring, as dx. Now what is the area of this thing? A very easy way to understand the area of this ring is to break the ring at any point. Let's say you break it at this point and then stretch the ring. When you stretch the ring, you get a straight line that represents a very thin rectangle. So when you cut the ring at a point and then you stretch it, you get a rectangle, and the area is going to be length into width. So we know what width is. Width is dx. Length is the periphery, that is 2 pi into x. So the area of the ring becomes equals to 2 pi x into dx. Now what is the charge on the ring? The charge on the ring will be dq equals to sigma into area, and that we are going to substitute and find out in the next page. So moving on, this is our ring. This is the point where we have to find out the field, point P, and as I told you, we need some thickness to it. You can't just take a thin ring and be done away with it. You need some thickness because you need to find the area. We also discussed what was the area of the ring. Small area was 2 pi x into dx. We also discussed what was the charge on the ring. Small charge, that is why dq. So that was sigma into area. Now what was sigma? From the disk we remembered q upon pi r squared into what is the area? 2 pi x dx. So you notice pi and pi is out of the scene, they cancel out. Q upon r squared, or 2q upon r squared x dx. So this is the charge on the ring. Now we all know the result for field due to a ring. We all know that. What is the result of field due to a ring? The field for a positive charge is along the axis of the ring, and its value is k q. Let's say this distance is something, but we don't know what the distance is, so let's call this distance as a, and the radius of the ring was obviously x. So the electric field due to a ring was kq a upon a squared plus x squared power 3 by 2. That was the field due to a ring, or that is the field due to this ring, and it is always along the axis. In case of positive charge, please notice, in case of positive charge it will be away from the ring, and in case of negative charge it will be towards the ring. So we are taking positive charge right now, so by general assumption it is towards the ring. So that is your field. So we start substituting. What is the charge on this ring? What is the q of this ring? So q of this ring is obviously 2q upon r squared, and then we have an a, and then we have an a, yes of course, and then we have an x dx, and then we have a squared plus x squared power 3 by 2. How do we integrate this? We know that this distance is x, this distance is a, and let's assume that this angle is theta. So we have a very good relationship here. X is equals to a tan theta. and we also have dx is equals to a sec squared theta d theta, and then we'll have to change the page. So this was the ring and this was the point. This was a, obviously this was x. The thickness of the ring was very small, that was dx. I'm not going to repeat it again and again, but we know that the value of field was 2 k q a x dx upon r squared x squared plus a squared ka power 3 by 2. That was the electric field due to the ring. And we knew that the electric field is along the axis away from the ring if we are taking a positive charge. And we also know here this was tan theta, so x was equals to a tan theta and dx was equals to a sec squared theta d theta. We'll try to replace all of this here. E equals to 2 kq a, obviously, and what is x equals to a tan theta, and what is dx equals to a sec squared theta d theta, and that is divided by r squared, and again we have x squared plus a squared ka power 3 by 2, that is a cubed sec cube theta. So we will throw out the useless things here. You can see 3 a's in the numerator and 3 a's in the denominator, so that gets out. 1 of the sec square theta and sec cube theta, 1 sec theta gets out. So you'll have E equals to 2kq upon r squared sin theta d theta. Now in order to find the total field, we'll have to integrate this particular result, and here in this I'll show you both the things. I'll show you the ring as well as the disc. So this was the disc and this was the ring, and okay, so here we had the points. Now let me draw it with, so this was theta if you might remember correctly, and this distance was x obviously, and this distance was a obviously, and the field was in this direction. So we can say that, we can very safely say that as we take the other rings, let me show you a few more of them. As we take the other rings and other rings, oh, I have disturbed my rings. Anyways, as we take the other rings, we will notice here that the theta angle, let me show you with a difference, the theta angle will keep on changing. Can you see that? The theta angle will keep on changing. So the theta angle is variable, and the theta angle changes and it goes to a maximum of, let's say, alpha, which is the highest point on the ring that covers the periphery of the ring. So theta is varying from 0 and it goes to alpha. So the maximum value of theta is alpha. So remember what was the field equals to? The field was 2kq upon r squared sin theta d theta, and we integrate it, and now you do remember from where do we integrate it? We integrate it from theta to alpha, so theta to alpha. So what is the integration? I'm sorry, we integrated from, let me remove this, we integrated from 0 to alpha. So you'll have 2kq upon r squared into 1 minus cos alpha, where alpha is the maximum angle. You can see the maximum angle here. We change the values of k here. K is 1 by 4 pi epsilon naught. So you'll have you'll have E equals to 2q upon 4 pi r square epsilon naught into 1 minus cos alpha. And over here you can say that q upon pi r square, q upon pi r squared was basically sigma. So I'll try to write it at the top here. It will be sigma by 2 epsilon naught into 1 minus cos alpha.